I'll just do it that way then. Okay, guys, is everybody out there able to hear me okay? I see some webcams and some microphones on and everything. So I have started recording, and I think I'm going to go ahead and get things started here. We've got about 15 people here, so we're missing a few, but hopefully everybody's on their way over. Welcome, guys, to our second week of the semester. Just going to make a couple quick announcements, and then we're going to be pretty proof heavy today. We're going to be talking about cardinality again, and there's quite a bit for us to kind of plow through on this. So I appreciate your patience with this in advance a little bit. But before we get into that, just a couple of quick announcements. I'm glad that you all found your way over to Zoom again. Just to remind you that we are going to do Zoom this week, so today and Thursday. But then starting next week, like 1 week from right now, unless something goes terribly wrong, I will be back in Fullerton. So we'll be meeting in the classroom next week. I'll remind you about that over the weekend in case you've gotten into some habits to come into Zoom. But next week, I am going to be back. In the meantime, for this week, again, just like last week, it's going to be all in Zoom, office hours, class in Zoom. As I'm still over here at my parents' house trying to help them kind of rehabilitate a little bit from the surgeries that they had a couple months ago, which, by the way, they're doing much better. So I'm pretty sure a week from now, I can safely make my way back to California. Anyway, for this week, there is a homework assignment due on Friday, just like there was last week on Friday. So you can be working on that. Maybe some of you already are started on it. I'll be around to answer questions, of course, about that if you need help during office hours. I've got those later on tonight, as well as Thursday night and Friday as well. So plenty of time to stop by and talk to me, or you can shoot me an email and I'll try to answer your email if you have anything that you'd like to check in with me about. I did grade the first homework assignment already. You probably noticed that I posted the solutions to it. So in Canvas, there is a folder that says homework solutions, and I'll be publishing my solutions to the assignments each week. Just keep in mind, of course, that this is a somewhat subjective subject in the sense that, exactly how you write up a proof can vary a little bit from one person's preference to another. So if you look at my solutions or how I wrote up some of the proofs and the homework, it may not be exactly what you wrote down or exactly the way you thought about it. So of course, you're always welcome to ask me to directly look at something you wrote, and I'll be happy to kind of assess that and make sure that what you wrote is just as good as what I wrote. Or to explain anything from those solutions. On that first assignment, I actually had time to grade all of the problems. I usually won't be able to do that. I'll have to pick and choose kind of randomly what I have enough time to grade. But with the first assignment, I did sort of look over everything. I gave people some credit just for turning in the assignment. I think on this one, it was 3 points that I gave everybody. Just for turning it in, and everybody got all of those points. But then there was also, each problem I tried to actually read your proofs and give you some feedback on those. And so I'll do as much of that as I can. And then in places where I don't have time to really carefully grade everything, I will post those solutions for you again. So anyway, so for this week, the homework is mostly out of section 1.3. It deals with functions. There's a lot of questions in there about images and pre-images that we talked about last time. And again, this is still kind of review material that we're talking about here. So I'm not dwelling on it for very long. And if you do need a little more extra help, by all means, feel free to stop by my office hours, and I'll be glad to do that. So anyway, does anybody have any questions before we kind of jump in here today?
Yes, Dr. Annan. For
Please.
assignment 2, it says due on the 30th, this Thursday.
Oh, that might have been a typo on my part. I meant for it to be due on the 31st. I'll fix that in Canvas if I need to. But obviously try to shoot for the 30th so you can ask me questions by Thursday if you have any, but I can let you work on it through Friday. Was that helpful to have Friday to kind of wrap things up?
Yes.
Yeah, because I figure a lot of you are like busy on Thursday, like for example, listening to my lectures. They maybe don't have time to work on homework that much on Thursday. So Friday is a little bit slower day usually, at least it is for most of the math department classes. So yeah, you can turn it in on Friday and that will be fine. I do want to point out that the next homework, which is homework number 3, is a little bit shorter. And I'm going to ask you to do that one kind of on a quicker turnaround. So over the weekend, I'll have you work on that. And then I'm going to have you turn assignment 3 in next week on Tuesday instead of the end of the week. So at some point I wanted to kind of shift to a Tuesday due date. So just keep that in mind. There's a little quick turnaround between homeworks 2 and 3. Any other questions so far?
So when you grade the homework and you don't
Yeah.
grade all the problems, will we
Not every time. Yeah, it's too much for me to do that. I mean, it takes a while to really, especially with this type of material, to really read everything that everybody wrote. On the first assignment, I was able to do it, and I will always grade as much as I'm able. So just bear that in mind. I'm going to pick and choose homework problems to grade. I kind of do it on the fly, to be honest with you. Like I don't know ahead of time what I'm going to ultimately choose. So just do all the homework. I'll pick some of them to grade and then ask you to ask me or check the solutions for anything that I didn't have a chance to look at. Fair enough?
So will our grade be based on the ones that you graded only?
The correctness part of your grade will be. Now, I also I give you some points, usually not very many, but I think I gave 3 points out of 20 on the first assignment just for turning in a complete assignment. So, if I happen to grade all the problems that you did, but then you skipped half the assignment, you will lose some of the points for the completeness portion of it, even if everything was correct. Does that make sense?
Yes, thank you.
That's how it's going to work. Hopefully that'll be a good way to get everybody to do all the problems. And again, I am going to try to grade as much as I can. We have about 20 students in this class, which actually is not a huge number overall. So that might help me to be able to do a little bit more this semester in terms of giving you guys as much feedback as possible, which is what I'm going to do. Any other questions? Okay, great. Well, in that case, why don't we go ahead and get back to where we left off? I know it was 5 days ago, but we had talked about functions last week. We talked about one-to-one and onto functions, which of course together makes up what's called a bijection. In fact, one of your homework problems for this Friday is to prove that if you take 2 one-to-one functions in a row and compose them together, you'll still have a one-to-one function. Or if you start with 2 onto functions in a row and you compose those together, you'll still have an onto function. And therefore, if you start with 2 bijections and you compose them, you still get another bijection. These are not difficult things to prove, but they're kind of important. In the background of everything we're doing, of course, functions are going to play a big role. And today in particular, we're going to be talking a lot about bijections. Bijections, okay? So actually, the first thing, before I go into the full recap over here, I want to give you a little trick having to do with bijections. So maybe over in the side of your notes, you can kind of write this trick down. And what I'm talking about here, because we're going to need to use this, is that if we have a function that's one-to-one, so let's write it down this way. If f, let's say going from x to y, is 1 to 1, then we can actually, it might not be onto yet. It might not be onto, but there's a little trick that we can use that will make it onto. And the trick is that we can shrink the codomain down so that the codomain exactly matches the range of the function. right? So then we can make a bijection. Let me call it G. And G will go from X, not to Y, but to the entire range of F. So from X to F of X as such. So in other words, what you're doing, guys, is, and I'm sorry, and this is via G of X equals F of X. So the way that you, and this would be for all little x in capital X. So the way this works, guys, just so it's very clear, you're just shrinking the codomain down. The original codomain of the function was y, right? But if you just sort of strip away the part of the codomain that does not get hit by arrows coming from the function, if you just remove anything from y that's not in the range of f, then you'll leave yourself with essentially, it's the same function. G is the same function as f. You can see that here, g of x equals f of x, right? It's the same function, but the main point here, is everybody able to see all of that? Let me know if you can't see anything on my screen, by the way. I can't quite see the whole thing from my picture here, but I think it's probably still good. G is the same function as f. The only thing that we changed is what the codomain of G was. So instead of the entire capital Y, right, which the function f might not be onto the entire capital Y, but guys, f will be onto whatever it's onto, right? So whatever the actual range of f is, right, then you will force G to be onto by simply taking the original codomain and shrinking it down to whatever the range of the function is. So it's just that simple. So you can take, so this is an important idea, guys. You can take a function that's one-to-one, and you can always view it as a bijection. You can view it as a bijection from the same input space X, but now to a codomain which has been shaped to be exactly the range of the function. Okay, so you're kind of cheating. You're making it onto by just choosing the codomain to be equal to the range. Okay, so that's kind of a nice trick that you're going to see me using that today. So I thought it would be worth kind of pointing that out. And again, bijections are the story of the day as far as what I'm going to be talking about, because we're going to talk about cardinality. And again, just to remind you, this is in the last section of chapter 2 in our book. And so two sets, A and B, have the same cardinality. We wrote this down last Thursday. We write this with the A twiddle B if there exists a bijection from A to B. All right, so that's the definition of two sets having the same cardinality. Try to get the idea of counting numbers of elements out of your mind, as that's not really an effective way of talking about cardinality for infinite sets. So all day today, I'm going to be using this A twiddle B notation. I'm going to be talking about bijections between sets. That's really where the definition starts from. Okay? By the way, I have my chat box open again today. If you've got anything you want to throw in there, a question, a comment, a concern, or whatever, feel free to do that. You're also more than welcome to unmute yourself and just throw out a question for everyone here. That's also totally good. Okay. Yeah, so towards the end of class last Thursday, we talked about the facts that I've put on the board here. Every set will always be in bijection with itself. You can just create like an identity function. So A always twiddles A, right? So that's this little twiddle notation, just means that there is a bijection from any set to itself, okay? And it's just a trivial function, right? Secondly, if there's a bijection from A to B, then there will be also a bijection from B back to A again. And this is just simply what is better known as the inverse function. The bijection that you use to sort of go from B to A is created by just turning the arrows around on the original bijection from A to B. What I mean by that is the correspondence is still the same, but which side is the inputs and which side is the outputs just gets reversed, right? That's the only thing that's happening there. So it's pretty easy to sort of believe that fact as well. And then finally, the third one is actually the one that I just alluded to from the homework that you're doing for this week, which is that if there's a bijection from A to B, and if there's another bijection from B to C, then you can make a bijection directly from A to C, and that is the composition of the two bijections. So in the homework for this week, you guys are going to prove that, yeah, if you compose two bijections together, yes, you'll get another bijection, right? So that's kind of the important point here. Okay, I just realized maybe I would be better off if I pin myself on there for the sake of the recording here. Okay, great. So those are the facts as we have them so far. Now in Thursday's class last week, I kind of finished off with a little teaser for you here. I gave you 3 examples of sets that have the same cardinality. And it's a little bit unintuitive because the sets don't maybe look like they would have the same size. But I am wondering, does anybody want to help me with this? If I take the entire real numbers and I compare that with the interval that consists of 0 to infinity, which would be just the positive real numbers, can anybody think of a function, a bijection, that would take a real number and turn it into a positive real number? You can use your microphone, you can put something in the chat. Again, no need to worry about, don't worry if it's right or wrong or anything like that. We're just exploring, we're just learning together a little bit here.
Absolute value.
Okay, so absolute value is certainly a good thought because that'll take a real number and replace it with a positive real number. I see in the chat somebody wrote down x squared. This is another good idea because if you square any number, it always becomes non-negative. Now we do have to be a little careful with x squared because if you plugged in 0, actually this would also be an issue for the absolute value function. If you plugged in 0, which is one of your real number inputs, the output would actually be 0. Is 0 included in this open interval? No. Remember from last week we reviewed the interval notation. So we're not including the endpoints of one of these open intervals. So at a minimum, we would have to tweak these examples. The other thing is, would the absolute value function be 1-to-1? Would 2 different inputs always give me 2 different outputs? Maybe not, right? Maybe not. Maybe the absolute value of 5 is the same as the absolute value of -5. So that would be 2 different inputs getting mapped to the same thing. So I think we need to think of something a little bit different. I've got a couple more ideas in the chat. Somebody mentioned x squared plus 1. That will take care of the issue of trying to make sure that we can hit. Well, it's actually got the same kind of problems, right? With the 1-to-1 issue, right? So 3 squared plus 1 is the same as -3 squared plus 1. They're both equal to 10. Ayushi has an idea of just limiting the x to be greater than 0. And that is an interesting idea for how to make a function 1-to-1. If you have multiple inputs that are being mapped to the same output, you could imagine removing some of those inputs from the domain, okay? And so if we were allowing ourselves to remove the negative numbers from our set, Ayushi's idea that's in the chat would be fine. But in this case, I want the entire domain to be the real numbers. So I don't want to restrict x to be greater than 0. I want to allow it to be any real number, positive or negative. Does anybody else have an idea? It's actually a very simple function, but it's not the absolute value function, and it's not x squared. Hyunjun in the chat has an idea that's starting to get closer, the natural logarithm. Now, the problem with that function is that I cannot take the natural logarithm of a negative number. You probably remember that about algebra properties of logarithms. And so if my inputs are supposed to be all real numbers, then I'm not going to be able to plug negative real numbers into the ln function. But we are getting closer here. Does somebody else have an idea? Oh, Amber, thank you. You bailed me out. Exactly what I was looking for. The exponential function, that is exactly the one that I was thinking about. F of x equals e to the x. That is it. That is going to be a great example. I can plug any real number into that, but e to any power is always positive, right? And it is 1-to-1. It is 1-to-1 because if e to the x equals e to the y, then x has to equal y, right? It passes the sort of the so-called, if you draw the graph of that function, right, the graph of e to the x here on an xy plane, you can see that no y value ever shows up twice, right? This will pass any horizontal line test whatsoever that you might draw. So this is 1-to-1, and it's also onto, because any positive number can be achieved. Maybe I should be writing some of this down, for at least for this, because I know you've done this before, probably in Math 280, but let me put I'm gonna put a little star next to that, and I'm just gonna come over here, and I just want to make sure people can write these things up a little bit. You know, how do you write down that f is 1-to-1 and that f is onto? So let's just do this for this example. To show that the function is 1-to-1, you know, I might want to assume that f of x, we talked about the definition last week, we assume that f of x equals f of y, and then our goal is to show that x equals y. So I'll just add that here. We need to show, you don't have to write this down in your proofs. You don't have to write down what it is you need to show, but I think it's a helpful guidepost for us. So assuming that f of x equals f of y, we would need to show that x equals y. So what we have is, we have that e to the x is equal to e to the y. And based on that, how do you imagine that I'm going to now prove that x equals y? What kind of algebra could I do? Yeah, Ayushi's got the idea. If we, in the chat there, if we take the natural logarithm of both sides, then we can simplify this. So I can take the ln of e to the x, which would be equal to the ln of e to the y. And the ln of e to the x is just x, and the ln of e to the y is just y. So that would check that off, right? So this is a kind of a standard sort of proof of a 1-to-1 function, right? So assume f of x equals f of y, and then we just try to prove that x equals y. Awesome. Okay, and then we can also think about showing that f is onto. And I'll just remind you again, onto just means that everything in the codomain has a preimage, at least one preimage, right? So I would need to pick something over here in the codomain, which is the positive numbers. So I could say, let's let, maybe I'll use a different letter here. Let me just use Z, just so we don't confuse it with what we were doing in the first part of the proof. So we pick a Z that's in the codomain. It has to be arbitrary, guys. So people sometimes have trouble with writing proofs for 1-to-1 because they put the notation already in the form of something from the range. And that sort of defeats the purpose of what we're proving here, which is that if we take something that looks very random, right? Some very random thing, just Z, right? That we can find a pre-image for it. Does anybody have an idea what would be, so I'm gonna do this here. Does anybody have an idea how we would get a pre-image for Z? Well, what could we plug into this f of x function right here so that the output would be Z? Yeah, okay, a couple folks are putting this in the chat for me. This is exactly right. If we plug the ln of Z into this function, then we are gonna get Z. I'm gonna just erase for just a quick second here so that I can write this as e to the ln of Z, which is equal to Z. So there you have it. Now on this one, I don't know how Ayushi and Hyunjun came up with the pre-image, but you can do these in your head if you want. Like if you can pull a pre-image out of the sky without having to do any writing, there's technically nothing wrong with this. The skeptic out there is going to say, well, where did you get the ln of Z from, right? So you could derive that pre-image kind of on a scratch paper by just setting e to the x equal to Z and solving for x. But technically, that's not part of the proof. For Onto, the proof really just consists of finding the pre-image. We don't have to show how we found it, but we just present the pre-image and we just check that it works. So I've taken f of what I claim to be the pre-image of Z, and then I just show the math that it really is the pre-image of Z. And we're done. Okay, so here's a nice little write-up of showing that this f really is a bijection. And isn't that bizarre? Because after all, the real numbers is like twice as big as the positive real numbers. And yet somehow we can make a bijection between them. This is getting into the idea that cardinality with infinite sets is a little bit of a slippery subject. Okay, it's just the way it goes. Okay, is everybody okay so far? Any questions? I think Onto sometimes can be tricky because we have to cook up this pre-image out of the sky somehow. So if you need to go write out some scratch work to figure out, well, what is the right thing to plug in to get the function to spit out this arbitrary output, scratch work for this is totally fine. What you see here on my board is a very polished up version of these verifications. It would be totally reasonable to start off on a scratch paper or a scratch board and kind of work some of this out on the side and then present this polished solution. Okay, great. Let's look at these other quick examples here. I've talked about, so the interval 0 to infinity is in bijection with the interval from 1 to infinity. Does anybody have an idea? I'll call this function g of x. Does anybody have an idea how I could take a number that's greater than 0 and spit out a number that's greater than 1? And don't think too hard on this one. We don't have to do anything too fancy. Put it in the chat if you think you might know. Let's just see what kind of ideas people have. Oh, okay, so something's coming in here. Yeah, just x plus 1, right? If we just take x and we just add 1 to it, that's going to get the job done. It's going to be 1 to 1. It's going to be onto. And so that's a real easy function. This function may not be unique. It may not be unique, so do keep that in mind. But this is definitely the most natural way to do it here. Okay, let's look at this third one. I'll call this one h of x. What I want to do this time is I want to take a number that's, I only want to work with positives, but I want to take a number that's bigger than 1 and replace it with a number that's less than 1. Anybody think of any kind of math function that would do that? Take numbers that are bigger than 1 and turn them to be less than 1. Yeah, Alyssa, thank you so much. That's exactly what I had in mind, just taking a reciprocal here, right? So you just take h of x to be 1 over x, and that's going to demonstrate again that this is a bijection. Now, somebody asked something in the chat. I just want to make a quick comment here. When you look at this function, h, it looks like the domain of that function would be any non-zero x, right? And yet my domain here is restricted to only x's that are greater than 1. So when I write down these functions f, g, and h over here, I have the understanding that my x's, my inputs, are coming from the set on the left side. It doesn't mean that maybe you couldn't expand the functions, especially in the case of g and h, expand the domain of these functions and have them, like g could be defined on all real numbers, yeah? But I'm restricting the domain to only be consisting of the inputs that I want, which in the case of g would be the positive x values. Okay, same thing on number 3. Although h would be defined for every non-zero x, I'm only going to allow myself to plug in x's that are greater than 1. So that's kind of the way to think about that. Okay, so those are 3 examples. Here is a 4th example now, which is that the real numbers are actually in bijection with the open interval 0 to 1. Okay, and this is by using well, it's really by using fact 3 above. Yeah, so if you think about it, the real numbers are in bijection with 0 to infinity. 0 to infinity is in bijection with 1 to 2, 1 to infinity, and then 1 to infinity is in bijection with 0 to 1. And if you compose all of these bijections together, you will get a function that takes a real number and spits out something between 0 and 1. What would that composition of bijections look like? Maybe I'll call this one j of x. Okay, so I'm going to make another function here that we don't have to do this, by the way, to prove the same cardinality. We can just use fact 3. But in case you're wondering, the way you could do this, guys, is you could start by taking e to the x, compose that with adding 1, and then take 1 over all of that. So this would be a way to put the 3 individual functions together in a composition that would now give you a j of x that gives you an output that's always in this open interval 0 to 1. Right, so that's kind of nice. If you can write down the composition of the functions that you're actually using there. Okay, so got some good examples going. Give myself a little more room over here. It's going to take me a second to clean this off. Oops. Any other questions so far, guys? Good. Okay, fantastic. Well, I'm going to introduce now a little notation that will help me with kind of what we're going to talk about here, this next proposition that's coming up. I'm going to use for every natural number n, so little n element of the natural numbers, what I'm going to do is I'm going to define this set j sub n to be just the positive numbers from 1 up through n. Okay, so we'll just Jn is just the set of the first n natural numbers. Okay, that's just a notation that the book is using. And I'm going to use that notation to make another definition here. And here's the definition. A set, capital A, is finite if, first of all, A is either empty or, so this definition has an or in it. The empty set will be considered finite. or A should be in bijection with one of these J sub n's. This would be for some n in the natural numbers. Okay, so what I've just put down, guys, is the definition of a finite set. And then, of course, the opposite of that, so I'll just add that here. If A is not finite, then A is infinite. So the opposite of a finite set would be an infinite set in this case. All right. Okay. So every set is either finite or infinite as a result, just depending on whether it's empty or in bijection. If I can make a bijection from A to J sub n. So that's it. All right. So with that in mind, I'm going to state a little proposition now, and this is in the book. So whenever I can, I'll try to tell you what numbers from the book these results are coming from. This is proposition 2.8, and this has 4 parts to it. This would be good flashcard material, by the way. It's just kind of nice to put these together in one place and be able to review them. The first one just says that if A is finite, and B is a subset of A, so if B is I'm sorry, that's not correct. That's not what I meant to say. Sorry. If A is finite and A twiddles B, that's what I meant to say, then B is finite. Be sure to let me know, guys, if you can't read any of this. I'm trying to use my board as wisely as I can, but I also need to make sure you can read it. So if A is finite and A twiddles B, then B is finite. That's what we're saying right there. Okay. Awesome. Let's do the second part. I'm going to write down all of these parts first. This part says if B is infinite, and A twiddles B, then A is also infinite. All right. So this is just saying that if two sets twiddle each other, they're either both finite or they're both infinite, right? If there's a bijection between two sets, then if one of them is finite, the other must be finite. If one of them is infinite, then the other one must be infinite. Now I'm ready for the 2 parts about subsets here. So the next one is that if A is finite, and this is what I was writing down earlier, which was a little premature. If B is a subset of A, what do you suppose I'm going to say if I have a subset of a finite set? What do you imagine might be true? It's still finite, right? That's what Amber's trying to tell me. Yeah, exactly. So then B is finite. A subset of a finite set is still finite. Absolutely true. And last but not least, number 4, if B is infinite, and if B is a subset of A again, then A is also infinite. Then A is infinite. So if B is infinite and it's contained inside of A, then A is also going to have to be infinite. You know, my comment about this is that there's A's and B's in different places, and I could see if you're trying to memorize where does the finite go and where does the infinite go and which one is A and which one is B, that could be tricky since there's 4 parts here. I think it's almost better to just understand these results more from I think you just need to internalize them conceptually. Guys, if you take it something that's infinite and you put it inside of something that's a superset of it, then the superset is still infinite, right? Or if you start with something finite and you make it smaller, well, then it's still finite, right? So just intuitively, finite means small, infinite means big. And you can kind of just use that together with this whole subset idea to understand how this proposition works. So if you're worried about memorizing, I hope I get the A and the B right and the finite and the infinite right on all of these. There is kind of an easier way, which is to just kind of think about common sense with this, and you'll probably get it right. I am going to write down the proof of this though, which does have 4 parts. Let's see how well I can go through the proof of these parts. This is going to give us a chance to practice the notion of same cardinality and so on that we have up here. So let's start with the proof of the first part. And so for the first part, I'm going to assume A is finite and that A has the same cardinality as B. So A twiddles B here, right? And this assumption, which is that A is finite, actually leads me to 2 cases, right? Because if you look at the definition of finite, what is it? A is empty or A twiddles J sub n for some n. So we talked about this last week when we have unions, right? When we have an or kind of statement, we tend to break those into cases. So let me just do a case 1 here, which is that A is empty. Okay. If A doesn't have any elements in it, guys, then guess what? If A twiddles B, then B has to be empty as well. You can't have something in one of the sets but not the other and expect to create a bijection. This is almost like a technicality. Like I don't even generally talk about having a function when my domain is empty. Right? Right? If I created a function and I said any I don't even know. I can't even think of a good example. But if you had some empty set and you were going to use that as your input space to a function, it just wouldn't make sense. So this case you could almost just fluff it off and just say, it doesn't really make any sense. The more interesting case would be the second case, which is A twiddles J sub n for some n in the natural numbers. Based on that, I'm wondering if anybody knows how I'm going to prove that B is finite. I have to prove that B twiddles basically a J sub n again, right? But what do we know? We know that A twiddles B, and we know that A twiddles J sub n. It seems like we could put that together with some of these facts over here, right? Yeah, there's some facts that would be relevant here. So what I can do is I might use 2 and 3 above. So in those facts 2 and 3, what I could do is I could say, look, B twiddles A, that's by fact 2. So if A twiddles B, then B twiddles A. And we already know that A twiddles J sub n. And so specifically by fact 3, now B would twiddle J sub n. So that would be it. That would be the whole thing. Okay? Is that clear to everybody? So fact 2, technically this is where 2 is being used to switch the order of the A and the B. So I put the B first and then the A. Not a big deal, really. All of these sets twiddle each other. It's symmetric, it's transitive. Just using these facts, you immediately get the conclusion that you want there. Okay, fantastic. Let's look at the second bullet point of the proposition. If B is infinite and A twiddles B, then A is infinite. Isn't that pretty much just rephrasing the first part? It's actually just rephrasing the first part, guys. So what we could do is we could do this one by way of contradiction. Right, by way of contradiction, I'm gonna use BWOC. I'll probably do that all semester long, by way of contradiction. If A is finite, or if A was finite, if A was finite, well then take a look. We just proved that if A is finite and A twiddles B, then B is finite. So then by part A, which we've just proved, by part A, right, B is also finite. But of course, for part two, that's not what we're saying about B. We're saying that B is infinite in part two. And you can't be both at the same time. So if B is finite, then it can't be infinite. So this is a contradiction. That is a contradiction. So the second statement is really just a rephrasing of the first one, if you want to think of it that way. Okay, hopefully that's so far so good, guys. Let's go on to the third part. Clear this off a little bit for you. The third part of this proof is actually the hardest part to write down. So I'm gonna need a little bit more room to do this one. So we're gonna start right here with part 3. So this one's slightly trickier. I'm going to assume in part 3, hopefully it's still readable, assume that A is finite and that A is a subset of B. Okay, so I'm sorry, I got that backwards. B is a subset of A. Assume A is finite and B is a subset of A. I want to prove that B is finite. Okay, so again, there's two cases. Case 1, right, this would be A is empty. What's the only possible subset of an empty set? How about the empty set, right? Okay, so then B is also empty, right? It's pretty much trivial to conclude that. Any subset of the empty set has to be empty. So we're really more interested in case 2. And for case 2, I'm going to again start off with A twiddling J sub n for some n in the natural numbers. Right. Okay. This time, what I need to be aware of here is that the B is not necessarily going to twiddle J sub n. B is a subset of A, which means it might be smaller, and so it could be some smaller J sub, I don't know, K that the B is going to twiddle. So to really get a handle on this, I actually am going to write down the bijection. Remember that this notation just means that there exists a bijection. So there exists a bijection. I'm using a backwards E for there exists. I'll call my bijection F that goes from A to the set 1, 2, ... up to n. So I'm actually explicitly writing out what J sub n is. Okay. So what I'm going to do now, guys, is that this function has a domain that is all of A. The entire set A is the domain of the function, but B is part of that, right? B is a subset of A. And so if we just kind of forget about all of the other elements of A, except for the ones that are in B, we can consider a new function. So here's what we're going to do, guys. We can consider a function G that goes from B to the set 1, 2, ... up to n via g of x equals f of x. So this is similar to that little trick I was talking about at the start of class today. I'm defining essentially the same function. The inputs and outputs works the same way as it did for f, but I'm only going to plug in, right? I'm only going to plug in the elements of b as inputs. So we call g the restriction. This is just a terminology, guys. G is called the restriction of f to b, and this is denoted, so I'm just gonna write it this way, guys. G equals f with a bar subscripted by b. So this is a pretty standard notation in function theory. I can restrict the original bijection f down to this function g, which has a new domain, right? The new domain for g is just b itself. It's not the entire big set A, it's just b itself, okay? Now the point here though, guys, is that note here, guys, g is still 1-to-1, okay? It's still a 1-to-1 function. So let's go real careful with this. Remember that f was a bijection. A bijection is both 1-to-1 and onto. So this function g will still be 1-to-1. Why am I not saying that it will still be onto? Well, it won't be onto because I've made the domain smaller. I have less arrows coming out of the domain than I did with f, because b is smaller than a. It's a subset of a. So there's less inputs to g, which means there's also less outputs. And so if f was onto this set from 1 through n, g is not necessarily going to be able to do that. So I'm not going to say that g is onto, but it is still 1-to-1. Different inputs have to be mapped to different outputs. That much we can be absolutely guaranteed of. Okay, so if g is still 1-to-1, you ready for this? This is where the trick comes in from the start of class today. Remember the trick? If you have a function that's already 1-to-1, but it might not be onto, you can make it onto by just shrinking the codomain. Exactly. Hyun Jung's got it. Exactly. We can just shrink the codomain. And so what will happen is that B will twiddle G of B. Okay, whatever the range of G is, we can now view that as the output set that's in bijection with B itself. And G of B is, of course, inside of Jn, right? Because, guys, the outputs of G are the same as the outputs of F, and the outputs of F are all in the set 1 through n. So that means that G of B lives as a subset of J sub n right here. Let's just actually give some names here to this G of B. Let's just say, let's write G of B. We don't know what it is, but it's got some numbers in it. x1, x2, up to, let's say, xk. We don't really know exactly how many elements it has in it, but it's something like that. And that's going to be in a perfect bijection with 1 through k, which is what we've been calling now J sub k. This would be for some k less than or equal to n. There we go. Okay, so thus B, which twiddles G of B, also twiddles J sub k, and hence by the transitive property, B twiddles J sub k, and so B is also finite. That took a little bit of work. We had to use the better part of this whiteboard to kind of write that whole thing down. Let you guys catch up with me there if you need to while I erase for a moment here. Everybody okay with that part? That's the trickiest part of the whole proof, to be perfectly honest. Okay, if everybody's all right on that part, I'm gonna quickly say something about part 4, the last part of this proposition, which just says that if B is infinite and if B is a subset of A, then A is infinite. Anybody have an idea how I'm gonna prove that? Amber, I can't hear you. I know you're saying something. Yeah, by way of contradiction, exactly. We can see that that Ayushi's got that in the chat as well. It's gonna basically look like the part 2. It's just gonna be like part 2, right? By way of contradiction, right? If A was finite, then by does anybody know why I wrote by little a down here? I was just looking at that. Shouldn't that have been 1? I was trying to say for part 2, I was trying to use part 1, right? These are parts 1, 2, 3, and 4. I don't know why I wrote A there. You guys are maybe wondering what that was supposed to be. I'm so sorry. This was supposed to be by a 1 here.
I
By
think
part
we
1.
understood it. It was
Yeah.
just,
Yeah, that was just me being silly. I don't have any idea why I wrote A there. Who knows? The weather's cold outside. What can I say? Maybe that's screwing with my brain. Okay, that should have been a 1. Anyway, this one is supposed to be by 3. So by part 3, if A was finite and B is a subset of A, then B is finite. But we're assuming that it's infinite, so that is a contradiction. So that would be a contradiction. So that's the end of that proof. That's all you have to say for part 4 as well. Okay, perfect. Sweet. Any questions, guys, on that particular result? Again, for the most part, everyone, this should just be intuition. It should just make sense to you when you think about what finite means and about what infinite means. Why do I go to the trouble to write out all the proof of something that's kind of intuitively clear? It's because we are early in the semester. We haven't done a lot of proof writing together, and I thought this is a pretty reasonable place to practice a little bit. We got some good ideas here about how to express some of these ideas for these proofs. So I just thought it was worth doing that. I'm gonna state another proposition right now, and then we are gonna take a 10-minute break here in a moment. But let me at least state this next proposition so that those of you who want to spend 10 minutes thinking about it can do so. And then we'll come back and we'll talk about it together. So this is proposition 2.9, the very next result. I'm just gonna state this one. This one also has a couple of parts. This has only 2 parts this time, but this is also very important. So if A is finite and there exists, I'll use a backwards E for that. If there exists an F that goes from A on to B. By the way, sometimes for onto, you'll see mathematicians will use like a double arrow here. Can you see that? That's a double arrow, like it's really hitting onto B. So if you start with a finite set and there's a function that maps it onto another set B, then B is finite. Okay, so that's the first result that we're gonna prove after we take a short break. And then the second result, as I'm sure you won't be surprised, is what about a one-to-one situation? So in that case, we have to turn everything around. So for part two, we're gonna start off with if A is infinite. So if we start with an infinite set, and this time if there exists an F that is one-to-one. Now, guys, for one-to-one, you will sometimes see mathematicians kind of draw the arrow like it's a fish hook arrow. It's got a little hook on the back end of it here. That's also kind of a fairly standard way to write the notation for one-to-one. You don't have to use it if you don't want to. I will always spell out the words of what I mean. But just in case you're wondering, sometimes a one-to-one function would be written that way. And so then in this case, if A is infinite and we have a one-to-one function from A to B, then B is infinite. Okay, so a super analogous result to the first part. Okay, so these two things, that again, they kind of go together. Yeah, so I think what I'd like to do is let you chew on those for 10 minutes. It's just a hair after 2 o'clock right now. So at about 10 after 2 or so, in about 10 minutes, I'm going to be back and we'll prove these results. But again, it's a 2-hour class and I always want to give people a chance to step away for a few minutes and kind of rest their minds. So why don't we take a break? And I'll see you back here at about 2:10. Well, guys, if you're out there within somewhere near the sound of my voice, in about another minute or so, I am gonna get things rolling again. So this is a good time to make your way back over towards wherever you're cozied up to my whiteboard here. All right, I think I'm gonna go ahead and try to push on here. Does anybody have any questions yet about anything we did here in the first half of the class today? Just kind of working with this idea of bijections and what infinite and finite sets look like. It's really what the main point has been so far. And we've got this proposition here. We've proven it already. And we're going to actually be using this proposition to prove the next one, which is why I didn't want to erase it quite yet. I'm hoping I'll be able to keep it up here just long enough to do this proof. So yeah, let's come back and think about this proposition 2.9. At some point, it would be great if these two results also fell in the category of intuition. Right? When you take an onto function, right, in order for a function to be onto, right, the set B cannot be larger than A, right? So if A was finite, you would expect B has to be finite. This is for an onto situation. And then on the other hand, for a one-to-one situation, it's kind of the other way around. For a one-to-one function, again, I'm just talking about intuition for a minute. For a one-to-one function, it wouldn't be possible for B to be smaller than A. If B was smaller than A, you'd have arrows converging almost guaranteed. And that would imply that it's not one-to-one. So for a one-to-one function, you kind of expect the sizes of the sets to look like this. So if A is infinite, then for a one-to-one function, B should also be infinite. Okay, so these pictures are just intended to kind of get you thinking about it correctly. This is maybe not quite as intuitive as the proposition we did earlier, but it should make a lot of sense, I think, as you think about it a little bit. Okay, but as you know, pictures don't count as proofs, so I'm actually going to erase the pictures for the moment and try to give a little proof of these two parts of this proposition. So the proof. Of course, I'm going to go one at a time with this as well. I'll start with the first part. So what that means is that I'm going to assume that A is finite. And that F is a function from A onto B. So F is going to map from A onto B. So just setting up my assumptions from the first part of the proof here. And we need to show that B is finite. And remember that there's two ways that could happen. B would be finite if it was the empty set, or if it was twiddling some J sub n, right? That's what finite means. So I'm just going to go ahead and assume, I'm just going to say we may assume that B is not empty. See, if B is empty, then we're already done, right? An empty set is automatically finite. That was part of the definition. So I can go ahead and assume that B is not empty, knowing that otherwise we would already be done. But here's what we're gonna do, guys. Here's what we're gonna do. What we're gonna do is we're gonna look at each, I'm gonna create a function right now, okay? And how am I gonna do it? Well, I'm gonna create the function actually with inputs from B. Notice that the F maps from A to B, but I'm about to create a function that goes from B back to A. For each little b in capital B, right, we may pick some element that I'm going to denote as A sub B that lives in capital A, such that F takes that A sub B and sends it to B. So for every element of B, I'm going to find some preimage for it. I'm going to find some element in capital A that F would send to B. Why am I able to do that? How do I know that I may, it says we may pick. How do I know that I can pick this element A sub B in capital A? Hey, Brian, you got it. It's because F is onto, right? So let's just add that, right? This is since F is onto. Absolutely true. So since F is onto, I can find a preimage. Now, this element that we have picked, this A sub B right here, it's not necessarily unique because I'm not assuming that F is 1-to-1 in this part of the problem. But all we need is any preimage. Any preimage for this little b, I'm going to call it A sub B, and F of that element is going to be equal to B. Okay, so guys, what I have just done is I have created a function that takes something from B and spits out something from A. So let's write that down, right? So we have a function. I'm going to call it G, that goes from B to A via G of little b is A sub B. So I'm actually making a new function that goes from B back to A again. And I would like to note that with this function, which is, it turns out that this function G is 1-to-1. I want to stop and make sure everybody believes me. Could there be two different inputs? Could there be a B and a C? And could it be that G of B and G of C are the same thing? You know, so let's just, maybe a picture actually would help here with the intuition. So here's A, here's B. We have F going this way. And for every little b here, I am looking back over here for a preimage, right? Could the preimage of C, if there was another element over here, let's say it was C, could the preimage of C also be this same A sub B? You know what, guys, if that was possible, F would not have been a function, right? You would have had two arrows coming out of the left side, mapping to two different elements of B. It's not possible. So you cannot actually have any other, say, C, where G of C is the same as G of B, right? So this is 1-to-1. This is 1-to-1. Different elements of B have to have different preimages in capital A. That's all we're saying by that comment. Okay, so guys, thus G is I'm going to use that same trick that we talked about earlier. G is a bijection from B to G of B which is a subset of A. So there is a bijection, it's a one-to-one function. It may not be onto, but it is onto whatever it's onto. Right? So the G might not be onto all of capital A, but whatever the outputs of G are, whatever the range of G is, that's called G of B. That will be a bijection from B to G of B, which is inside of A. Okay, so let's see, where are we here? A is finite. That's the assumption. Assume A is finite, and what do we have? We have a subset of that, right? A subset of a finite set. Do we know anything about that? We look over here, I tried to keep this up on the board. If A is finite and we take a subset of it, then the subset of it is still finite, right? So if A is finite, so I'm just gonna say by proposition 2.8 part 3, G of B is finite. Because A was finite and we have a subset of it. G of B is finite, but it is in bijection with B. And we have something about that also. If we look at the first part of the proposition over there, if one set is finite and it's in bijection with something else, then the other set is also finite, right? Awesome. So if G of B is finite, then thus this one is by proposition 2.8 part 1, B is finite. And that's exactly what we wanted to prove. There you go. That's going to do the proof. Awesome, awesome. Everybody following this? It's kind of a clever idea. You take the elements in B and you can just create a function that goes in reverse. That goes back to A again. And that allows you to set up this bijection from B back into a subset of A. So the function here, there's a question that Ayushi is asking me in the chat, which she said, well, what if F was not one-to-one? So, if you had, say, an A1 and an A2 here, so this is capital A and this is capital B, and you map this over here like this. So you have two different elements mapping to B. Well, then when you're defining this function G that goes back from B to A, you have more than one choice for what your A sub B is. You could choose it to be that guy or that guy. And either one will work. There's not a right or a wrong answer to that. So that's kind of how that works. We don't need to worry. Even if F fails to be one-to-one, this proof still works out just perfectly. Yeah. Okay, great. What about the second part of this proposition? We're going to do this one pretty quickly. Actually, this part is not too bad. I'm going to assume here that A is infinite and that we have F one-to-one function from A to B. So is everybody able to read all that? Good enough for now. I'm basically just restating the assumptions of the second part of our proposition here. And we need to show that B is infinite. We're going to show that B is infinite. Well, as it turns out, guys, this is just a one-liner. Okay, so this is just a one-liner, because what we're going to do is we're going to have, I'll just say it this way, since F is one-to-one, we have A in bijection with whatever its range is. So again, I'm using that same trick. So if anybody needs help with this, for your notes, just so you can refer back to this later, I gave you that little trick at the start of class today. I'm using it right here. So there's a bijection from A to whatever A is onto, which is its own image, right? But this, of course, is inside of B. the image of A would be, or the range of the function is a subset of B right now, okay? So guys, A is infinite and it twiddles f of A. So f of A is also infinite. That's, I guess, part 2 of the earlier proposition. If one set is infinite and it's in bijection with another, then the other set is infinite. And if that's infinite and we take something that is a superset of it, then the superset is also infinite. That's actually part 4 of the previous proposition, with the roles of the A's and B's changed a little bit. So let me just wrap this proof up then. It's already done. We just maybe should write a little bit here. So I'll just make a note, since A is infinite, so is f of A. That's f of A, and that's by proposition 2.8 part 2. And then we're gonna take a superset of that. And so B is infinite by proposition 2.8 part 4. That's right. So that wraps up the proof. You're really going back to proposition 2.8 to finish that argument off. Okay. That all right with everybody? Ask a question if you want to. I'm more than available for that. Just be careful when you're applying this proposition 2.8, you understand the roles of the A's and the B's are being swapped around a little bit, right? Specifically, like when you use part 4 here, you're saying that f of A is infinite and it's a subset of B, so then B is infinite. So the roles of the A and the B in the statements have to be kind of modified, but that's basically it. There's a question in the chat about proofs. Do you need to write down all the proposition numbers for all of these results? Certainly when you take an exam in this class, I will not be expecting you to have memorized what the proposition numbers are. It's helpful for you in your homework to do that, I think, so that you can make a reference back to it in the future if you want to review something that you did in one of your proofs. But it's not absolutely critical. You know, if you know the result and you can find it again without having specific numerical references, that's okay. I like to put them in my proofs so that people can look back and just remember where they came from. Okay, one more proposition here, guys. I know there's a lot of proofs today. I guess this is a proof class. So it makes sense that we would have a lot of these to do. This one is a bit of a fish out of water. It's kind of a different result. This one just says that the natural numbers is infinite. Again, this is another one of those statements that probably seems extremely obvious, but I am actually going to write a proof of this. We have a formal definition of what infinite means, and so we're going to use it. And I'm going to do this by way of contradiction. Let's assume that the natural numbers was finite. Assume that n is finite for this first sentence here. Let's suppose that the natural numbers somehow manage to be finite. Obviously, it's not empty. We know the natural numbers are not empty, so then if it's finite, then the natural numbers is in bijection with, and in other words, it twiddles j sub n for some natural number n. Okay, and so we have a bijection. This gives a bijection. And I'm going to call my bijection f again, going from, actually I'm going to go I'm gonna set up the function in the opposite direction. It doesn't matter, right? Because there's a symmetry to these bijections. So I'm gonna take the inputs to be from J sub n and the outputs to be from the natural numbers. We don't know what the bijection is. We have to live with this abstract idea that there is a bijection there, but I can't say anything more about f. I don't know what f of 1 is. I don't know what f of 2 is. I don't know what any of those values is. But what I can do is I can point out that the entire codomain must be consisting of the range of the function. So this is what onto means, essentially. If a function is onto, it just means that if you take f of everything in the domain, you get the entire codomain. And what is f of everything in the domain? Well, that's just the set of f of 1, f of 2, and dot, dot, dot up to f of n. That's the entire thing. Okay? Again, this seems so blatantly obvious that this is going to be a contradiction. I only have n numbers listed here, and yet I have that equal to the natural numbers. This is crazy, right? This is like no way that this could be true. How am I going to explain what's wrong? I'm just gonna go in this list here of n things. I'm just gonna pick the biggest one, okay? And then I'm just gonna add 1 to it. Okay, so I'm going to find the largest element in this set. Let's just give it a name. Let's just say it's f of k, right? And this is a k value that's somewhere between 1 and n. So for some value of k between 1 and n, there's some largest value, right? And note, I'm just going to note here that if we take that number, f of k, and we add 1 to it, so I'm just going to go a little bit bigger now. I took the largest element of the set and I added 1 to it. So that is no longer an element of the natural numbers, so apparently. Because you've taken the largest thing from this set, and if you add 1 more number to it, it's not in this set, which is equal to n. Okay, so that's a contradiction because this is a natural number, my friends. This is some natural number that you added 1 to. Okay. Oh gosh, somebody is calling my phone right now. Are you guys still with me? Are you able to see this okay? Okay, good. I'm gonna keep talking. Somebody's trying to call me. Anyway, this is a contradiction. That's going to be a contradiction. Okay, so that's the end of that proposition. All right, very good. So the natural numbers is infinite. No surprise. All right, I hope you guys are hanging in there okay. I promise I'm generally very energetic and excitable running around the room, but right now I'm kind of sitting here in this chair trying to get through this stuff. It turns out that when you think about all of the infinite sets that are out there, this is really the smallest one. It's kind of smallest, I'll put that in quotes. You can't really get a smaller infinite set. So when you think about all sets, I'm just gonna draw a little picture here, guys, to kind of illustrate this. You have the finite sets, and then you also have the infinite sets. So every set is either finite or infinite. And what I want to talk about now is that we're going to sort of talk about different sizes of infinity. And the sizes of infinity are going to be, first of all, countably infinite. And then the even larger size of infinity is something called uncountable. So a set can be absolutely uncountable.
Oh, Dr. Anna, we lost audio. I think.
How about now? Can you guys hear me?
Yeah.
Okay. Somebody decided to call my phone and it took me away from my screen. I couldn't see myself. And so I wanted to try to get rid of that voicemail or whatever, and it caused me to screw something up. So anyway, I'm back. Good. Okay, perfect. So I haven't really said much. I was just trying to get myself working again. I'm going to define what I mean by countably infinite and uncountable next, okay? And we only have about 15 minutes here to go. We're not going to get too deep into all of this today, but I do have a definition that is pretty important. I hope you guys are starting your piles of flashcards by now so that you're able to start memorizing some of these definitions. There are going to be a lot of them, a lot of definitions in Math 350, okay? So this is definition 2.12, and it's just what does it mean to be countably infinite? So A is countably infinite. A is countably infinite if A twiddles the natural numbers. So any set that we can make a bijection to the natural numbers with, that is what we mean by countably infinite. Okay, so that's kind of the small size of infinity. And then, of course, the second part of this definition is just going to be what does it mean for A to be countable? So A is countable. A is countable if A is finite or countably infinite. So countable just means finite or countably infinite. Okay, great. And then thirdly, uncountable just means, well, not countable. Okay, so the third thing here in this definition, A is uncountable. Uncountable if A is not countable. Right. Okay, so uncountable just means not countable. Let me give you the intuition behind this first, and then we'll start getting some examples of this. Guys, if something is countable, let's actually do countably infinite. If something is countably infinite, it actually means that even though it's infinite size, you can actually create an algorithm to list all of its elements. There is a first element, a second element, a third element, a fourth element. For an infinite set that is countably infinite, we can list the elements. Just like we can list the natural numbers. 1, 2, 3, 4. And if you keep going, you'll hit every natural number, right? An uncountable set is one that is so massive that if you just start trying to pick off a first element, a second element, a third element, a fourth element, and go at it like that, you'll actually never convince me that every element in the set ended up getting listed. That you actually identified every single element. So there's actually quite a big difference between a countable set and an uncountable one. I'm gonna come over here and write down an example or two. Get some examples going. And then we'll definitely be picking this back up on Thursday. We're not gonna finish all of this topic today. It's a pretty big topic. So here's an example. Call this example 1. Yeah, so if I take 2z, this is countable. I used this example briefly last week. These are the even integers, right? And if I'm claiming that this is countable, I'm actually going to give a proof of this. Again, what does countable mean? Let's not lose track of our definitions too quickly here. Countable just means it either has to be finite. Well, that's not finite. All even integers is not finite. The other possibility is countably infinite. Countably infinite means there needs to be a bijection. That's what this twiddle is, right? There needs to be a bijection here between the set and the natural numbers, right? Well, I can convince you, hopefully I can convince you that the even integers are countable by producing a bijection for you. That's exactly what I'm going to do. So I'm going to define f to go from, we can go from, well, normally I will go from the natural numbers and map them to the set. I'm going to try to create this bijection for you via f of n equals, oh, you know what, guys? This is not what I want. I'm so sorry. I want not the even integers, I want the positive even integers for now. I'll generalize this in a minute. So what I'm talking about here, is everybody able to read that? Let me just get this clear enough. I want to talk about the positive even integers. Not all even integers. I'll come back to a larger example in a minute. But if I just take the positive even integers, can somebody tell me what function I'm going to use here? F of n equals what? I have to spit out something that's even and something that's positive. Let's see, I lost my chat box here. Let's get this open again. I've got a couple people. I'm getting the same answers from Hyunjun and Ayushi. 2n. What do you guys think? Do you think that'll work? I think so. I think that's going to work great. That function will be a bijection from the natural numbers to the positive even numbers, right? Namely, f of 1 equals 2, f of 2 equals 4, f of 3 equals 6. So the outputs that we're getting are 2, 4, 6, 8, and so on. And that's a bijection. It is 1-to-1, and it is onto. So f is a bijection. I'm not going to check that again right now, but technically, if this one would be considered clear that this is a bijection at this point. So I wouldn't even expect you to write that up. We could just sort of agree that that one's fairly obvious. Let's go on to a more interesting example though. Let's actually try to prove to ourselves that z, all integers, is countable. Okay. And if I want to convince you that the integers are countable, then I have to define a function that takes a natural number, a positive integer, and spits out an integer. And we have to do it in a way that will be a bijection. We have to make a bijection here. So whatever we write down has to be one-to-one and onto. Just to give you an idea of kind of the issue that you would run into, don't write this down yet, guys. You might think, well, I'll just define f of n to equal n. So f of 1 equals 1, f of 2 equals 2, f of 3 equals 3, and so on. But is that a bijection? No, it's not onto all of the negative numbers if you do that, right? F of 1 equals 1, f of 2 equals 2, f of 3 equals 3. But what value of f would give me -7? Nothing would work according to this function. So this is not going to work as the bijection of choice here. We have to be a little more clever about how we create this bijection. In fact, what we really want to do here, guys, is we want to sort of alternate between hitting the positives and hitting the negatives. So this is a little bit of a clever idea. I'm going to do the following. I'm going to define my function in a way that has a couple of parts to it. And I'm going to do sort of, well, one thing, let's just say over here, if n is odd, I'm going to do one thing. And if n is even, I'm going to do something else. What I'm basically going to try to do here, guys, is I'm going to use the odd inputs to hit the positive integers. And I'm going to use the even inputs to hit the negatives. See, one thing I can do for the evens is I can just say, look, I'll take my even number, I'll divide it by 2, and then I'll put a minus sign in front of it. If you think about that, what is f of 2? It's -1. What is f of 4? It's -2. What is f of 6? It's -3. I will continue to hit all of those negative integers with this part of the function, right? For any even input, I can divide it by 2, it'll still be an integer, and I can put a minus on it. Okay? And what I'm going to do is I'm going to use the odd integers to hit the positive integers. So my odd inputs, my odd natural numbers are going to hit the odd integers. And how am I going to do that? Well, here's what it turns out you need to do. You're going to take your odd number and subtract 1 and then divide by 2. Right? If you take an odd number and you subtract 1 from it, you get an even number that's positive, and then you divide that by 2, you still have a positive number. Actually, let's list out the first few values. What is f of 1? F of 1 is 0. And then what is f of 2? F of 2 is -1. Using the bottom formula, right? F of 3, we go back up here, we get 1. F of 4, we go back down here, we get -2. F of 5, we go back up here, we get 2. F of 6, we get -3. F of 7, we get 3, and so on and so on and so on. Guys, this is the list that I was explaining. When you have a countable set, you can list the numbers in a way that convinces me. Does this convince you that every integer will eventually be in the list somewhere? I mean, if I gave you the number 1 million, you might wonder, well, where is 1 million going to be? Well, I'm pretty convinced that it might take a while, but by staggering my enumeration of my integers, positive, negative, back and forth, I eventually will see 1 million show up in the list. And any integer is eventually going to be in this list. So this is what I mean when I say that the intuition of a countable set is that it is one that you can list all of its elements in an exhaustive way where everything does get listed. You're not missing anything here. So that's kind of a nice example. Guys, next time, I have to give you a reason to come back. Nobody's thinking about dropping this class yet, I hope. Okay, good. No, please don't do that. I really like having you guys here. What I wanted to say is that I usually like to try to give you a little bit of a teaser of like a reason to come back, something we're going to see next time that's going to be helpful. This one may seem like a really, really tough thing to prove, but we are going to prove on Thursday that Q, which is the rational numbers, is actually countable. Can you believe that? We can actually list every fraction in a way that will convince us that nothing's been missed. I mean, you think about how many fractions there are that you could make. It is so enormous. And yet somehow I can make an exhaustive list of every rational number. But as it turns out, I'll add one more thing here, guys, and then we're going to call it a day. If you try to press your luck and go all the way up to the real numbers, which is a bigger, even bigger set, this one turns out to be uncountable. That is so massive that it is not even countable. The way you will prove that one, I'll just to give you a heads up, you're going to assume that it is countable. You're going to assume that you've made your list, and then you're going to construct some number that was not in the list. You can actually make that happen. It's a beautiful argument called Cantor's diagonalization argument. So on Thursday, I will come back to this idea of countable sets. We'll give some more examples of countable and uncountable sets. We've got a big, big theorem we're going to prove on Thursday. So yes, please hang in there. Make sure you're getting enrolled in the class if you're not already, but I'm really excited to do this stuff with you guys. I have office hours tonight and Thursday night and Friday night, and I would love to see you there. Otherwise, I think that's it for today. Does anybody have any questions? Okay, well, thank you for taking the time to tune in, and I will see you all on Thursday, if not before. Bye for now.
Oh, Professor,
Yes.
can you add me back to the Canvas? I don't see it.
Okay, I'll do that for you.
Thank you.
You bet.